Okay, so we're in section 5.7. We're being recorded now. And we talked about additional techniques of integration. For instance, trigonometric integrals using trig identities are helpful in regards to those. And then we talked about partial fraction expansions. We did an example, and now we're going to do another example. So let me give you a moment to copy this example down. Okay, let me see, there was something. Yes, David, that's correct. That's correct. Well, yeah, David's asking about on the test, multiple choice for one question. Yes, it's not like the homework. Obviously, the number of tries is limited, and multiple choice is very limited, right? Some multiple choice you might only have one try for, but for many problems, like certainly the ones where you type in the answer, you'll have multiple. You'll have at least 3 tries. All right, no problem. You're welcome. So, okay, here we are. We have this integral. We have an integral for a rational function. And it is necessary to take the rational function, which is 2x squared minus x plus 4 over x cubed plus 4x, and use a partial fraction expansion. Now, what do we have to do with the denominator when we do a partial fraction expansion? What do we always have to do with the denominator?
Factor.
Factor.
That's correct. We have to factor that, and we know x cubed plus 4x can be factored, right? So, all right, let's go ahead to the next page where we have our solution. And indeed, we can factor an x out of x cubed plus 4x. Okay, so take a moment here and then this is the partial fraction expansion down here. Let me give you a moment to copy, and then we'll talk about it. Okay, so, well, now in this case, we have a linear factor. Okay, when we factor the denominator, we get x times x squared plus 4. So in this case, we have a linear factor and we have a quadratic factor. So the linear factor, we take those factors in the partial fraction expansion, and we have the sum of 2 fractions with the denominators, one being x squared plus 4. So what do we then put in the numerators of the fractions? Well, since x is a polynomial of degree 1, above the x we put a constant, because a constant is of degree 0. So what goes above in the numerator has to be of one less degree than the polynomial in the denominator. So like for the second fraction, you see there's an x squared plus 4 in the denominator. Well, that means the numerator would have a linear expression, b times x plus c, because that's of degree 1. And degree 1 is 1 degree less than the quadratic factor in the bottom. Okay, so that's how we would expand this. Okay, and of course, what we have to do is this hold on here, rational equation. We're going to multiply through. Let me just see here. Where's my? Hold on. Put this in here. Yeah, this rational equation. We're going to multiply through both sides by the least common denominator, which is x times x squared plus 4. And of course, nice things happen. Nice things happen here. Simplification on the left, which again gives us on the left 2x squared minus x plus 4. And then by simplifying on the right, you will get a times x squared plus 4 plus bx plus c times x. So I mean, this should be hopefully pretty obvious, but you know, I can write it out a little bit. So you have a times x. On the right side of that rational equation, you have a times x times x times x squared plus 4 plus bx plus c over x squared plus 4. And that all gets multiplied by x times x squared plus 4. And so simplification occurs on the right. So we'll get a times x squared plus 4. And then more simplification over here. That'll give us bx plus c times x. Are there any questions up to this stage here? All right, very good, very good. Well, so now what we want to do is we want to expand out the right side. So I'll distribute the a, I'll multiply it by x squared and by 4. And I'll distribute the x by multiplying x by bx and by c. And then I'm going to get this expression below. And what I want to do with the ax squared plus 4a plus bx squared plus cx, you know, with this part right here, is I want to group together like terms. Well, ax squared plus bx, right? The ax squared plus bx squared. I can factor an x squared out. All right, and so I write then that is the quantity a plus b times x squared. And then I have cx plus 4a. Please let me know if you have any questions. So how many variables do we have to solve for here? How many variables do we have to solve for?
3.
3, that's right, Tosh. 3 variables. So looking then at this last equation here. If there are three variables, we need three equations. So 2x squared, if the polynomial on the left equals the polynomial on the right, then 2x squared would have to equal the quantity a plus b times x squared. So this would mean then that what would a plus b have to equal? What would a plus b have to equal? That's right, Nathaniel. It would have to equal 2. That's right, Sandia. Well, it's sort of like, let's take an analogy, David. Suppose you had a plus bx equals 4 plus 3x. Let's just take this is now a whole separate little kiddie example, but it'll help you, simple example, but it'll help you. If a plus bx equals 4 plus 3x, what does this tell you about the value of little a? What will little a have to equal? Have to equal 4. Okay, good. What would little b have to equal? Have to equal 3. So it's the same kind of thinking here. Same kind of thinking here. I have a polynomial on the left. Hold on here. I don't know why that's doing that. I have a polynomial. I'm talking now this last part, this last step here, last equation. Polynomial on the left equals the polynomial on the right. Well, if the two polynomials are equal, then the terms of the polynomials have to be equal. So yeah, so 2x squared would have to equal a plus b times x squared. So that means a plus b would equal 2. Good, okay. Well, what about negative 1x and cx? What's that tell you about c? What would c have to equal? Negative 1, that's right, Jinghoon. Okay, and then finally, we have 4 here. We have 4 here, and we have 4a here. So what would 4a have to equal? That's right, 4. Okay. And so a would equal 1. That's right. So those are your three equations. Those are your three equations with 3 unknowns. You have them now. You have the 3 equations with 3 unknowns, and you can, well, you already know what c is, and since a equals 1, b would have to equal 1 as well. And so you know, I mean, I got this all like laid out here, all laid out there. Okay, and so now the rational function 2x squared minus x plus 4 divided by the denominator x times x squared plus 4, that's going to equal 1 over x, because 1 is the a value, plus 1x minus 1 over x squared plus 4. Let me just see here. I want to do that a little more. Hold on here. Yeah. So 1 is equal to a. B equals 1. And c equals negative 1. And now you have your partial fraction expansion. And of course, we are taking the integral of the sum of two fractions. That's the sum of two integrals. And what we can do here on the right-hand side is this C was equal to -1 based on, in the partial fraction expansion, in the partial, hold on, let me, right, the -1x. In the partial fraction expansion, -1x, we set -1x equal to cx. And so that's how c was equal to -1. Okay? Sandia? Okay, very good, very good. Okay. Well, so now this fraction here, x minus 1 over x squared plus 4, that fraction, we can split that up into these two fractions. You know, we're doing what we need to do so we can get our antiderivatives. And I can certainly split that fraction up into those two fractions. It's no different than saying, you know, if I have like 4 minus 1 over 7, that's equal to 4/7 minus 1/7, which is 3/7, by the way. 4 minus 1 is 3, right? So it's no different, this process. And then we get down to here. We get down there. So let's look at these integrals here. What's the, I mean, is this first integral, what's the antiderivative of 1 over x?
ln of absolute value of x.
That's correct, Tosh. The natural log of the absolute value of x. That's right. So the first run, Sandia, almost right. Just need the absolute values around that x, but you have the right idea. First one's good. That's no problem. Let's look at the second integral. Now the second integral, would we use integration by parts or substitution for this one? Good, good. What would we do? Mario thinks a use substitution. Good. What would the use substitution be? That's right, David. That's right, Sandia. Use substitution. Yeah, let u equal x squared plus 4. And I'm going to show this on the next page, but I'm just kind of, you know, looking a little bit at the integrals to see what I got here. Now the last integral, this one here, is going to require a formula for. And the formula is available in section 5.7. So let me go to the next page here. Okay, and this is what we laid out. And there is a formula in section 5.7. It's formula 1. It's there in the book. If you look in your ebook, in section 5.7. That formula comes right before example 5 in the book. Okay, and it's actually example 5 that we're doing. So this formula, the formula says that the antiderivative of 1 divided by x squared plus a squared is equal to 1 over a times the arctangent of x over a plus a constant. And that formula you will have access to on your exam. I'll make sure you have access to that formula. And the formula is derived using a procedure called trigonometric substitution. But we're not going to worry about that today. You'll have that formula on the exam. Well, 4 is equal to, what is a equal to? Well, 4 is equal to 2 squared. And so a equals 2. And, the u substitution here is on the second integral. It's pretty clear. X squared plus 4 equals u, and x times dx is just 1/2 du. And so we get down to this step here, and then it's pretty straightforward, I think, finishing the rest of it. But let me know if you have any questions. Okay. All right, who's feeling good so far? Okay, very good. Very good. Taj is good. And okay, well then, so the final answer is then, well, we have it, but there, our antiderivative is for this rational function. It's amazing. It's the log of the absolute value of x plus 1/2 times the log of x squared plus 4 minus 1/2 times the arctangent of x over 2 plus a constant. Now notice here, for the log of the absolute value, here before I had the log of the absolute value of x squared plus 4, but I can drop the absolute values. Why is that? Why can I drop the absolute values and have these parentheses here for the x squared plus 4? That's right, Jing-sun. It's always going to be positive x squared plus 4. Always going to be positive. So WebAssign would accept this answer, or it would accept that answer there. So now you've seen two partial fraction expansion kinds of problems, and they're very important for like differential equations. I've seen them in multiple classes, but definitely Math 282 differential equations. They're very important. They're involved in finding inverse Laplace transforms, for example. I want to be, let me see here. Well, I'm going to say they're used in Laplace transforms. Let me say it that way, okay? In that whole content area, so you need to have a little more experience with these partial fraction expansion type problems. The appendix, okay, there's an appendix G in the back of the textbook. Okay, remember, let me just see here. Let me bring up that ebook. One moment here. Just go here to the ebook. Okay, so there's the ebook. And if we go to the appendices, okay, we talked about there's a trigonometric appendix, but also there is an appendix on appendix G there, integration of rational functions by partial fractions. So there are going to be a few problems in your homework, the one that's due Sunday, from that appendix G. And it gives a more, the appendix G gives a more thorough treatment of the partial fractions. I'm going to cover I'm going to cover another case that I think will be helpful for you. And let me see here. One moment. Let me bring up. Actually, I guess I have to. Let me see. I think I have it here. Let me see. I think. Yeah, here we are. Yeah, here's a new example. Now this example would be something you would see in Appendix G. So what you're going to be doing is in your homework, the partial fraction expansion problems, the ones that are due on Sunday, the majority of them have watch it videos or master it, some kind of help aid. So you're going to be fine. But I think doing, with the example I just did and then doing this new example, you're going to have a pretty good feel for doing partial fraction expansions for the problems that we're going to do. So let me give you a moment to copy this example down. Okay. And then we'll talk about it. Okay, so we're doing a definite integral, and of course the denominator, we always look to see if the denominator can be factored, and clearly it can. The x cubed minus 2x squared, that's a factorable denominator. But before we do this, normally what we would do is we would factor the denominator and write out the partial fraction expansion. But in this problem, notice that the numerator and denominator have the same degree. Those polynomials have the same degree. The problems that you have seen so far are problems where the degree of the numerator in the rational function is less than the degree of the denominator. Okay, the polynomial in the numerator is of degree less than the polynomial in the degree of the polynomial in the denominator. That's what you've seen so far. But here we have a situation where both polynomials in the numerator and the denominator have the same degree. So in this situation, we cannot do partial fraction expansion yet. What we have to do is actually, we have to divide. We have to divide the polynomial on top. Okay, the x cubed minus 2x squared minus 4, we have to divide that polynomial by the polynomial on the bottom. And this is the case when you have a rational function and the degree of the polynomial on the top is greater or equal than the degree of the polynomial on the bottom, you first have to do long division. That's correct, Sandhya. So let me show you this. So on the next page, I do this long division. I do it right here. But what I do here first is, how many remember doing long division in pre-calculus or algebra 2? How many remembered that? Okay, good. David and Sandhya, and it's something I've taught pre-calculus. It's something everybody should have done. But if it's been a while, let me just make an analogy here. So let's say you were to take 20 and divide it by 3. Okay, well, all right, so 20 goes inside here. This is a little different. Synthetic division is covered in pre-calculus. This is a little different than that, but I know what you mean. 20 divided by 3, very good. 20 divided by 3, 3 goes into 20 6 times. So 6 times 3 is 18, and you have a remainder of 2. So 20/3 equals 6 with a remainder of 2. But that means we can write 20/3 as 6 plus 2/3, right? We can take the remainder of 2 and put it over what we're dividing by, 3, and we can write 20/3 as 6 plus 2/3. Okay, well, the analogy is the same when we're dividing a polynomial by another polynomial. We're taking x cubed, we're taking x cubed minus 2x squared minus 4, and we're dividing it by, okay, x cubed minus 2x. So x cubed minus 2x, x cubed minus 2x squared. So x cubed minus 2x squared goes on the outside here, and x cubed minus 2x squared minus 4, that's going to go on the inside here of the, of the box. But of course, where is the x term? Well, the x term is just 0x. So I don't forget to include that, right? And now I say, okay, well, the highest power is x cubed in both of these polynomials, and x cubed goes into x cubed 1 time. So I put a 1 there, and 1 times x cubed minus 2x squared is x cubed minus 2x squared. I'm going to subtract that, and I'm going to get cancellation, and I'm left with the remainder of -4. This process is no different than dividing 20 by 3, no different. So we can write then this quotient of the polynomials then as 1, as the 1, right, the 1 here, minus the remainder 4 over x cubed minus 2x squared. Exactly the same process as when we divided 20 by 3. How many find that helpful, that little analogy there when I had 20 divided by 3? Does that help you feel comfortable? Okay, good, Mario, good. Good, excellent, good, Xavier, excellent. Okay, well, so now let's continue. Now notice this remainder, well, or this, I want to be careful, as the 4 divided by x cubed minus 2x squared. The 4 is of less degree than the denominator. The 4 in the numerator is of less degree than the denominator. So we're ready to roll with partial fractions. But I have here the integral of a difference. I have the integral of a difference. And I can write that as the difference of the integrals. Okay, I can write that as the difference of the integrals. And so the first integral, that's no problem getting the antiderivative. But the second integral, the 4 over x cubed minus 2x squared, there we're going to need to do the partial fraction expansion. Are there any questions before we go to the next page? Okay, well then we'll go to the next page. So again, this is now the integral that we have to figure out. So, okay, well, as always, we factor the denominator. So x cubed minus 2x squared factors as x squared times x minus 2. But x squared can be written as x times x. So, if we were to completely factor the denominator, as far as like completely factor it, we can write x squared. We can write this x squared as x times x. So in this case, what you get is what's called a repeated linear factor. And this happens in differential equations a lot. You have a repeated linear factor, or let me just say a repeated factor in the denominator. So how do we then write out the partial fraction expansion? Well, so you might think that okay, well, the partial fraction expansion, I'll write this, but you don't write this. Partial fraction expansion would be a over x plus b over x plus c over x minus 2. But that's not the case, because x is a repeated linear factor. You see, if you just have, like here, b over x, you could combine a over x plus b over x. And so you don't get independence. So this is not, when you have a repeated linear factor, how the expansion is. The correct expansion would be a over x plus b over x squared plus c over x minus 2. That's how you have to do it. That's how you have to do it. And incidentally, if you had, let's say you had something like this. Let's say you had 4 divided by x times x times x times x minus 2. Okay, what would the expansion be in that case? What would the expansion be in this case? Now you have a repeated linear factor 3 times. So First, you're going to have a over x. Then you're going to have b over what? B over x squared, right? And then you would have c over x cubed, good. Okay, and then plus d over x minus 2. Okay, so just keep that in mind. Keep that in mind. Right. So we can't ignore the repeated linear factors. We can't ignore those cases. We can't ignore when we have repeated factors of any kind. So okay, here's the partial fraction expansion, and so I have then this rational equation, and of course, just like I did previous times, I'm going to multiply by the least common denominator. Both sides of that rational equation, I'm going to multiply by the least common denominator, which is x squared times x minus 2. And then I'm going to do the necessary simplification. I'm going to get 4 on the left, and then I'm going to get all these terms on the right. Please let me know if you have any questions. Yeah, Jing-sun, the x squared, you just have to like when you have your partial fraction expansion, the fractions can't have the same denominators in them. Think of it that way. They can't have the same denominators in them. So you have to take the x on that second fraction and make it an x squared. It just is, and it will work out. It will work out. You see, you have an a, b, and c to solve for. And if the second fraction, if you had b over x, well then the a over x plus b over x would combine to like have one constant over x. And you wouldn't have 3 constants. Maybe that helps to solve for. You have 3 constants to solve for. And to solve for them, the denominators have to be different factors on the bottom. I don't know if that kind of helps give you an intuitive feel, but it is correct. Okay. If the denominators are different, yeah, I mean basically this example plus the 2 that I've shown you, I think, Jing-sun, you're going to be okay with the homework. Now there might be something a little new, but if there's something a little bit new, there will be a help aid available. If you're don't like, I know what you're thinking. You're thinking, man, there could be so many variations of this, but don't think like that. Don't think like that. Don't worry about that. If you are comfortable with what you're seeing here and what you're going to see in the homework, you should be, I think, okay. Okay, you should be okay in general. Okay, all right. You're welcome. You're welcome. Okay, so naturally, the right-hand side of this equation, I'm going to expand it out. Okay, I'm going to expand it out, which I do here. And I end up then, I group together like terms. So ax squared and cx squared, those are like terms. So that adding those would give me the quantity a plus c times x squared. And then the negative 2ax and the bx, those are like terms, so adding them together would give me the quantity negative 2a plus b times x. And then finally, you have negative 2b over here. And so the 4 on the left, well, the 4 can be thought of as, 4, you can write as 4 plus 0 times x plus 0 times x squared, right? And so matching the coefficients on the left and the right-hand side of this equation would give you that a plus c would have to equal 0. Negative 2a plus b would have to equal 0. And negative 2b would have to equal 4. So immediately b equals negative 2. Substitute negative 2 for b in this second equation, and you'll get negative 2a minus 2 equals 0. A will equal negative 1. And then take the negative 1 and substitute it in for a in the first equation, and you'll get negative 1 plus c equals 0, so c would equal 1. And now you have your partial fraction expansion, the specific one. And notice the limits don't change. The limits don't change. We didn't do a substitution. So that gets us down to here. I mean, it's really an amazing procedure, this integration by parts, and it's so important. So important. I've seen it in multiple courses. Okay, so this second integral here, okay, this second integral, right, can be expressed, well, we can distribute the negative through the integral sign here to the 3 terms. And so this would give us the integral from 3 to 4 of 1x dx plus the integral from 3 to 4 of 2 over x squared dx, then minus the integral from 3 to 4 of 1 over x minus 2 dx, right? Please let me know if you have any questions. And of course, I'm gonna write that integral as the sum of 3 integrals. Are there any questions on what I just showed you there at the bottom? Okay. Well, then let's proceed on to the next page. Okay, so here's where we're at. Here's where we're at, finding our integral. our definite integral. We got to compute these 4 integrals, and they're pretty basic, the antiderivatives for those 4 integrals. It's really, pretty basic. And you just then substitute in your 4 and your 3 and work the problem out. And in the end, the exact answer would be 7/6 plus the natural log of 2/3. So really, I'm going to just let you copy this. Please let me know if you have any questions. Okay, hold on. I see something here. Let's see. Sandia says, how did I get 4 minus 3? Let's see here. Oh, you mean here? Right, right here? Well, the antiderivative of 1 is x. And so I put in a 4 for x. And then I'm going to subtract. And then I put in the lower limit 3 for x. Because the antiderivative is just x. Is that okay? Okay, good, good. Very good, Sandia. Are there any other good questions? Okay, I'll give you another moment here. Okay, well, if you're good with this, I'll stop the recording. And let me stop the recording.